Okay, I decided to just have them all pre-drawn out because it was going to take really long to draw them and also talk about them. So, let me go ahead and see. So this should cover lots of the first couple parts of reabsorption. But first we'll talk about filtration, I suppose. So filtration is the process. If we have a little kidney over here, or a nephron over here. Our nephrons are the functional unit of the kidney. Right, I think each kidney has like 1.2 billion or million nephrons, I think. And so filtration is the process by which the blood gets filtered, right? And it goes into the kidneys. And there's a couple of different layers there that affect this. The first one is the fenestrated capillaries. Those have little holes that allow the hydrostatic pressure to push. Another pressure is going to be the colloid pressure pulling out this way too. And so that's going to make it go this way through the fenestrated capillaries and then through the basement membrane. The basement membrane has a negative charge, so most negative things won't get through, like big things, like lots of the amino acids and stuff. And then podocytes are the last filtration barrier for that. Then you want to reabsorb everything. So in your proximal convoluted tubule, you're going to reabsorb sodium with lactate, amino acids, glucose, bicarb. I didn't write on here. But you're going to have bicarb, and then you're also going to put hydrogen in exchange for sodium, but hydrogen is going to go back into the lumen. And all of these channels with sodium are all found on this side too, so that's how you reabsorb all of this. You're reabsorbing 100% of your glucose, 100% of actually all of those, but then only 70% of your water and 70% of your sodium. Then you get to your proximal tubule. This is where you get your anions coming in. The main point is just to get chlorine back in. So that's what's happening in the PET. Your descending tubule is not permeable to salt. So this is only taking water out, so that's why you're getting more concentrated. But then by the time you get to your ascending tubule, you're going to have this channel right here. It's the NC, N sodium, NKCC channel. And then you're going to get your potassium and your chlorine. Water is not permeable, so now you're going to get more concentrated, but you're putting all your salts out. And that's why it gets less concentrated up here. In your principal cells, these are the ones that are subject to hormones. ADH will bind and it will cause these aquaporin channels to be put on the membrane so you can get water reabsorption. Aldosterone is going to go to your nucleus and it's going to do some transcription there, and it's going to cause you to make more sodium and potassium as well as increase the amount of the sodium potassium pumps. Then you have your A and B cells. These are your intercalated cells. Your A cell is for your acidosis and your B cell is for when you're in alkalosis. In acidosis, you have lots of hydrogen, so you're trying to put hydrogen out into the lumen, and you're trying, I guess I should write that. This is the blood, and this is the lumen. So you're trying to put your hydrogen into your lumen, but you're putting your bicarb into your blood to try to counter the acidic. And then in exchange for hydrogen, you're doing potassium, which potassium will then leak out. In exchange for the bicarb, you're doing your chlorine. Then the cells essentially just switch based on which the membrane switches. So the channels are the same, but the membrane switches for your B cells when you're in alkalosis, because alkalosis is low hydrogen. So now you're trying to put hydrogen out into your blood to kind of counter that. So that covers, let's see, that's all of that. I talked about filtration in the renal corpuscle. I talked about the membrane, right? That's the podocytes and the negative charge of the basement membrane. The pressures involved, the pressures involved, you're just going to have that normal like glomerular filtration pressure, which is like the equivalent of like your HP or glomerular pressure or glomerular hydrostatic pressure. Then you have your glomerular colloid osmotic pressure, which is like kind of like your BCOP. You are not going to have a capsule osmotic pressure because there's no albumin, there's no proteins in there, at least there shouldn't be, so you're not going to have that, but you do have a hydrostatic pressure going this way. So the overall pressure of this is like 55, so you have your mesangial cells to kind of increase like strength and stuff there. Okay, that's the pressures. Okay, describe how blood flow may be regulated to the glomerulus. Okay, so in In your DCT, you have these macula-densa cells. And what they're doing is they're detecting your salt. And then right in here is where you have your afferent arterial glomerulus. That's your capsule. And so this can send signals. These macula-densa cells can send signals to your afferent arterial. So if your macula-densa cells detect an increase in your salt, what they're going to do is they're going to constrict the afferent arterial, because a high amount of salt going through means that you have a high GFR, and so you want to bring that back down, so you're going to constrict that. So it's like if you have a tube like this, what you're doing is you're constricting right here so that you can kind of lower it from right here, from where you're actually doing the filtering. Opposite of that is if you detect low sodium, you're having a low GFR, and so you want to increase it, so you're going to dilate it. That way you can have more blood coming through to filter. And then for your efferent arterial, right over here, what affects your efferent arterial is just going to be renin or angiotensin 2. Ang2 is going to constrict this as well, so that you don't have, oh, but this is in the state of like mostly like an emergency, like your blood pressure is like super, super, super low. But yeah, angiotensin 2 is also going to control that as well. GFR is going to be the rate at which you filter, and it's detected by a couple things. So your GFR is equal to your clearance. Your GFR is equal to your renal clearance, but that's only if your substance is something like inulin or creatinine. There's 3 rules. I'm just going to talk about them because I don't really want to write. But the first rule is that it cannot be made by the kidney. So the kidneys can't make or destroy it. It has to be freely filtered, and it can't be reabsorbed or secreted. If all of these follow, then your clearance will equal your GFR. So that's the glomerular filtration rate, which is just talking about the milliliters of plasma filtered or cleared of a substance per minute. So that's what renal clearance is talking about. So for example, if your renal clearance is talking about something like glucose for X, well then it should be 0 because you're reabsorbing everything. But inulin and creatinine, the normal level is like 125. So if you get something above that, then you're secreting. And if you get something below that, like if your creatinine level is like 80, well that means you're not filtering properly, or you have some kind of kidney damage, or maybe for some reason that's being reabsorbed. So your glomerular filtration rate is just talking about like, okay, how well are your kidneys functioning? But the way you can detect that is by using something that is just freely flowing through and you're not catching that at all. So that's what GFR is. Okay, renin-angiotensin-aldosterone system. Okay, so you have renin. Renin is released from your kidneys, and what it's going to do, it's going to take angiotensinogen into angiotensin 1, which is then going to go to your lungs. And in your lungs, there's something called ACE, which is your angiotensin converting enzyme. It's going to turn that into angiotensin 2. Angiotensin 2 is then going to do a couple of things. It's going to go do that vasoconstriction, that's the vasopressin, which is then going to increase your peripheral resistance, which will then increase your blood pressure. It's going to go to your pituitary gland, and in your pituitary gland, it's going to release ADH. ADH is going to increase your water reabsorption, and then it's going to go to your adrenal gland, I'm pretty sure, and your adrenal gland is going to release aldosterone, which is then going to increase your salt. And if you have salt, water is going to follow. So this is just to increase your blood volume, and all of that is going to increase your blood pressure. It asked what ADH and aldosterone does at the cellular level, which I showed up here. ADH is putting the aquaporin channels in, and aldosterone is increasing that sodium potassium pump. So often if you have aldosterone, you're going to have hypokalemia. All right, that's kind of how that one works. In part 2 of this essay, describe how loop of Henle is used to establish concentration. Okay. If I draw my nephron, nope. Okay. So this is my nephron. These are my levels. Up here is always 300, and the outside is going to match. But then when you get to your descending loop of Henle, right, you're taking out water, right? We know that. So you get to about like 600, we'll say. Okay, so you get to about 600. At this point, you're as concentrated as you can be as far as your salt goes. So your salt stays at that level of concentration inside here, okay? But because you get so concentrated, when you're about down here, you get permeability with another thing, which is your urea. So now you get double the concentration. So you get all the way down to about 1200 in your concentration right here, which is crazy. But then as you come up this way, well, now you got a pump, and now you're taking out your salt on your ascending loop of Henle, right? The NCC pump, and so that's going to start bringing you from 1200, you're pumping it all out, so now you're going to go back, right? And you're going to get to about 150. This is also permeable to urea, so urea is going to come out here, but then urea, thankfully, it's not just going out here, it's also going to go back in here, because that's how you protect your red blood cells, right? You're trying to protect your red blood cells, because otherwise they would shrink due to the hyperosmotic conditions that they're in. And so then you can also concentrate your urine even more, because if ADH is present, well, we know it's going to bind down here, and it's going to let even more water out, so then our urine becomes even more concentrated with salt and with that urea. And so then your pee is going to look very yellow. So if you have yellow pee, that means that you are dehydrated. But if it's clear, well, that means that ADH isn't present in your kidneys, so you're hydrated, and that is good news. So that's how all of that works together. Oh, and then the reason why this works is because your blood is going in an opposite direction. So your blood is going in this direction, but then your filtrate's going in this direction. And that's called the countercurrent multiplier system. So as your filtrate goes in this direction and pulls out water, right, you're getting it super concentrated, but then you pull out the salt to go into your blood over here, so then that's why you go back up. So that's your countercurrent multiplier system. I already taught like lots of this to Brother Hunt, so yeah, that's where I'm going to end. Thanks, Jordan.